Sunita ma'am, am I audible?
Sir, good afternoon, sir.
Good
Yes,
afternoon.
yes, sir. Sir, shall we wait for 3-4 minutes,
No,
sir?
no, no problem, no problem, ma'am.
Thank you, sir. Very good afternoon to one and all. Before starting of this session, I would like to take this opportunity to introduce Dr. Arunanshu Mahapatra. Dr. Arunanshu Mahapatra is presently working as an associate professor in Veera Surendra Sai University of Technology, Burla. He has published many international and national journals in reputed publishing houses like IEEE, elsewhere IET, Springer, etc. Dr. Mahapatra is a senior member of IEEE. His academic career is decorated with several reputed awards and funding. Dr. Arunash Mahapatra's contributions have acclaimed recognition from honorable subject experts around the world. Dr. Mahapatra has more than 20 years of industrial research and academic experience. Presently, his research team is working on research areas like localization of sensor nodes in indoor and outdoor environments, uh, in the spectrum sensing and allocation and 5G networks. Welcome you, sir. It's really our honor to have you as a resource person. I would like to welcome you all to our online AICT Hotel FDP program on quantum computation and information science. Now I hand over my this session to Arunanshu Mahapatra, sir. Sir, over to you, sir. Hello, sir. Hello, sir. Sir is facing some technical difficulties. Kindly be here for 2 minutes. I will join immediately.
Sunita ma'am,
Sir.
screen is visible to all?
Yes, sir. Yes, sir.
Okay. Fine. Good afternoon. Uh, Thank you, Sunita ma'am, for your invitation to share some of my experiences and knowledges regarding this quantum error correcting codes.
Thank you, sir.
Uh, so this any kind of error is always a challenge for an engineer or a technocrat or a researcher, irrespective of their domain of knowledge. So most of the research is always focusing on how to get quality information received. If we are talking about from the communication engineering perspective, that is, the quality of the service need to be maintained at any cost, irrespective of the discipline in engineering. This quality of service term plays a vital role to demonstrate the efficacy of any system. So this quantum computing as a whole may not be a new topic for us, but it is an evolving topic nowadays. People are talking about this quantum computing to communicate and to store more amount of information by sustaining the quality of the service. For our case, the quality of the service is nothing but talking about how exact information we are capable of communicating, or in form of any storing or something like that we can talk about. So since we are talking that some error is present or some error is getting introduced, so exactly from where these errors are coming and how these errors are affecting our system performance as a whole, and how to detect these errors and how to correct these errors are nothing but a different area of research, and that integrates different challenges for us. So if you'll see, either from storing perspective or from communicating perspective, I can say errors may be introduced by either the transmitter or by the channel. Here, the transmitter, I mean to say, is the source of the signal. So the source of the signal may be a device which collects some information from the real world scenario. Example, a transducer, let's say, for example, in common scale, if I want to say, the transducer is collecting some information, analog information, and it is converting to digital. Then whatever the thing that is in the process of quantum computing, that all the requirements it is meeting, and at the end it is capable of forming it in some qubits. So then from the transmitter to the receiver end, the receiver may be a storing device, or it may reproduce the signal, original signal. Maybe if it is a form of voice communication or any other kind of communication, that means if it is getting reproduced at the receiver side by using the reciprocal operation at the transmitter, that is also possible. That means from the source, between the source to destination, the medium, the channel is also introducing some amount of error to it. So many work has been done, that means from my knowledge, on how to take care of this channel noise. But most of the researchers are remaining silent about the errors that has been introduced by the transmitter. No doubt, the present literature says much about how coding can be done at the transmission side, so that at the detection we can get back our signal while maintaining the quality of the signal is sent by the transmitter. But the researchers remaining silent in most of the work, how the transmitter is behaving, and if the transmitter is misbehaving, then my protocol or my technique should detect that misbehavior and fix it there, so that the error that is going to be introduced by my transmitter should get nullified almost. I cannot claim that I will suppress all the errors, or I will simply eliminate all the errors at the transmitter side, but I could say, or I could claim, that 99% of my errors that is going to be introduced by the transmitter can be suppressed if I could have, or I would have, a better technology or protocol that can detect the faults happening in the transmitter side, so that a part of our headache, I should rather say, is eliminated there. Only we are going to concentrate on the channel then, because channel is not in our hand, it is a non-deterministic kind of thing, it's random. The behavior of the channel is random. If you are saying that it is wireless, then it is quite dynamic always. So first we'll talk about what the kind of errors that can be done. So many things are there. So if time permits, then I will elaborate, because in 1.5 hours, that is, time is very small. Anyhow, I will give some of the ideas about it. So what may be the sources of the faults in the transmitter? It ranges from the hardware problems such as poor connections. It happens is the age of the device is increasing. Definitely some connection related issues like your soldering, all the stuff that is present in that particular building block is giving some problem. Though the recent technology says that such kind of problems may not occur for a quite long amount of time, but there are some chances. We cannot ignore those chances. The probability may be 0.5% or less than, let's say, 0.0001%, but still some probability are there that will make the fault to occur. Similarly, some software faults. Software faults means the algorithm you have embedded may not work properly due to some reason. Maybe due to some security threat. Let's say some intruder has captured our device and trying to do some malfunctions by using our device, then the software may not behave properly. And definitely some inside noise will be present due to several reasons. I'm not going to elaborate all. And some residual energy. Why I'm saying residual energy? because nowadays most of the devices we are relying on, those are portable in nature, and the battery is the device. In if you say that is today's buzzword, that is Internet of Things. In the Internet of Things, we are having the foundation is a sensor network, and the sensors are operating in batteries, and so many battery operated devices are there. That's why the residual energy also plays a major role of introducing some faults. So if we are trying to classify these faults, this is the classification of the faults we have introduced. Me and my team has introduced, and it is published in IEEE journal. And what we have classified those faults, that is, the faults can be it can be crash fault. Crash fault means it's simply, that means once the fault appears, then it will continue forever. Then it is kind of omission fault. That means it is not responding. And timing fault means that is at a particular time, if it is not responding, then that is kind of there are several kind of faults are there. I'm not going in details of it, right? One of the very interesting faults that is related to your security is your authenticated Byzantine fault and Byzantine fault. Now, this all these faults can either be your hard fault or soft fault. Hard fault means it is fault related to your system hardware, and soft fault means sometimes in some literature they are saying that a soft fault means it is a computational fault. So, irrespective of their faults, based on the persistence, the faults can be categorized into three types. One is permanent fault, another is your intermittent fault, another is your transient fault. Permanent fault, as I told you, based on the persistency, it has been categorized. Permanent fault means once the fault appears, it continues forever till the fault is not attended. That is one kind of fault. And another fault, which is quite interesting and dangerous, is intermittent fault. Intermittent fault means the fault will appear for some period of time, and that fault will disappear. Again it will appear, again it will disappear. So the appearance time and disappearance time, in literature people are saying that they are following a distribution, that is Poisson distribution. That means while the fault appears, it will appear for an exponential amount of time, and when the fault disappears, it will also disappear for an exponential amount of time. But in practice, this is not exponentially distributed, but rather it is distributed, that distribution is following a variable distribution. So the variable distribution says that once the fault appears, then the frequency of its appearance gradually increases, and after some amount of time, the fault is becoming, or the fault is behaving as a permanent fault. So it is following not Poisson distribution, but rather variable distribution. So detecting this intermittent fault, that means how we can detect, because as I told you, if we could detect the fault at the transmitter side, so that the corrective measure can be taken, and we need not to bother about how to design a code to take care of these errors introduced by these faults. Only we would be concentrating on the errors that is going to be introduced by the channel. Because when both the errors are that is channel is introducing some error and your transmitter circuit is introducing some amount of error, that means your number of errors are increasing. So there is a chance that even though my coding is that much of efficient, but due to the large amount of errors introduced by the transmitter and as well as the channel, my detector algorithm may not be able to detect my signal back. So it may not be that much of efficient. That's the reason I'm giving my importance to at least nullify the errors that are going to be introduced by the transmitter block. So that means how can I eliminate it? By detecting the error. That means detection is required. If I will not detect the error, then how can I correct it? So if the fault is intermittent in nature, then detection of the error is a challenge. Because to detect any error, I have to apply a test to it. I have to test that system to detect an error. That is the fundamental principle. So then the question arises, when to apply the test, so that the application of the test and the appearance of the fault will coincide. When I apply my test and if the error is not present, then my algorithm will assume that the system is fine. But in practice and in actual, the system is having an intermittent fault. So then that is a challenge. People are working how to detect intermittent fault. That means we have to design a test pattern. That test pattern can find the intermittent fault by taking less amount of time. That means your detection latency should be small. Another very peculiar kind of error is called as your transient error introduced by transient fault. The peculiarity about this fault is the fault appears for a very small amount of time, maybe in form of millisecond, microsecond range, and the fault disappears for a long duration, sometimes maybe weeks together, or sometimes maybe months together. So in most literature, researchers are suggesting that a system suffering from transient fault should not be considered as faulty, because most of the time the transient fault occurs due to an abrupt change in situation or due to a small high intensity noise. Maybe for example, you can say while we are enjoying music in our transistor, if thunderstorm is happening, we are getting a very noisy signal for a very small amount of time. It doesn't mean that my receiver is not working properly, but it has been affected by a high magnitude noise. So that is an example or a good example of your transient fault. So these kinds of faults need to be detected, and if the fault appears, then the corrective measures can be taken so that the information source which is generating the information will be always giving an error-free information at the output of its or output of the information source. That means at the beginning a very part we have addressed. So this we have suggested that, as I told you, the intermittent fault appears for a particular amount of time and disappears for a particular amount of time. This is the model that we have suggested, that you can see. So it is initially we have designed it as a two-state Markov chain, having two states. One is called as your fault disappearance, another is called as your fault appearance. That means initially we'll assume that my system is fault free, and with some rate it may fall into intermittent fault, and once it having intermittent fault, then it will stay. That means the fault may appear for a particular duration of time, and the fault may disappear for a particular duration of time. As I told you, most of the literature, they are saying that that is your two states are having an exponential time to stay, but in practice that is not exponential most of the cases, but that is following a distribution called a variable distribution. So after some appearance and disappearance, as I told you, that this system will, and this will enter into, right? So this is the kind of mathematical model we can think about intermittent fault. Is behaving and how to take care of those transmission. Sundam, am I audible?
Yes, sir, you are audible, sir.
Screen is visible, na?
Yes. Like,
sir, it's black screen only. It's visible, sir. Now it's visible, sir.
Is it visible now?
Yes, sir.
yes, sir.
Right. Okay. Right. Now let's talk about this channel error, because a part that we have concluded, and I have not gone in details of it. So that may require, that is a different area of research, how to detect or how to diagnose the faults. That is an interesting topic to take care. Then next thing is that is next culprit or next contributor of error is nothing but your channel. So a signal arriving at the detector in a communication system whose occurrence is due to noise in the channel, that is the error generally introduced by the channel, because channel is having so many properties to play, or it may be when we are saying that some of the characteristics of the channel is now you can say due to channel we are having some errors, and the detector, that means we must have some error correcting code, so that at the detector we can detect my signal back. That is the case. So what are the quantum errors? If we talk about this quantum computing, the quantum errors may be in the qubits, or the qubit errors we can say. So it can be a bit flip. So it can be a phase flip, that we'll see how to counter all these things. And this may be due to decoherence, which is a major headache or major thing that is to be taken care, or it may be completely rotated by e to the power j theta factor. So these are some of the examples of single qubit errors, and how to handle those errors, because these errors are due to the things that we have discussed so far. That means we need to design some coding techniques so that these things can be addressed at the receiver. That means the receiver should be capable of getting back all those signals. So in the error correction, what is my problem? The problem statement says, when computing with a quantum computer, you cannot look at the computer, what the computer is doing. We cannot say all these things. We are only allowed at the output side. That means what it is giving back to us. So the result is what happens if an error is introduced during the calculation, because the computer is not allowing to participate in the computation as the end user or as in the protocol designer. Once we have designed the protocol, how the quantum computer is doing all these things, that is immaterial to us. And the solution is, we need some sort of quantum error detection, so that if some error is present or it is introduced by the source itself, then at the receiver, my receiver could able to detect those errors, and not only detecting the errors, but also it will find the position of the error, where the error is. That is nothing but the beauty of any error correcting code. So in classical scenario, let's store an unknown single bit for a time t. The errors is in a time interval tau. One error occurs with some probability, let's say p tau. So when the error will be, as I have told you, the error means if I want to store, in classical situation I am saying, when I am to store or transmit bit 0, the bit 0 may get flipped as bit 1, or if I want to transmit or store a bit 1, then it may get flipped to bit 0 in classical thing. So what may be the solution? It is simple solution. Let's represent this 0 not by a single bit, but multiple number of bits. It means, let's say now my 0 is represented as 0, 0 and 0. Similarly, your my 1 is represented as now 1, 1 and 1. Now this 0, 0, 0 is transmitted, and if at the receiver assume that one bit is in error, let's say the middle bit, it was transmitted as 0, but what I got, the middle bit is getting flipped, that means 0 is now becoming 1 due to the presence of noise. Similarly, let's say when I have transmitted 1, 1, 1, I received 0, 1, 1. So the simplest thing that I can do at the receiver is going with for your majority voting procedure. The majority voting procedure says whichever bit is in majority, the receiver is taking decision in favor of that. That means for this example, I can say I am having two number of zeros. So the receiver is taking decision in favor of 0. Similarly, since I am having two number of ones here, that means my receiver will take now decision in favor of 1. So this is the classical procedure of getting the things done. But in quantum computing, so this is called as a redundancy. So we are introducing some redundant bits to take care of the errors introduced by the transmitter as well as the channel. Though this redundancy is killing some amount of our spectrum or wavelength, the bandwidth, but still to get a better performance at the receiver side, so however, in quantum computing, this kind of replication is not possible due to certain things that we have to go for. Right? Whatever I have told you, that same thing is given here. Suppose errors in our physical system for storing or transmitting 0 and 1 causes each physical bit to be flipped independently with some probability. Right? In most practice, that means if we will say they are equiprobable, 0 can be flipped to 1 and 1 can be flipped to 0 for a long run, we can say that if they are equiprobable, that means probability may be calculated as half. That is a different thing to talk about. So we can correct the errors by using a redundant coding. By using this, that means now 0 can be stated as 0, 0, 0 or 0, 4 zeros also that is there. But for example, we are saying that 0, 0, 0 and 1 is with the state your 1, 1, 1 like that. Okay. So after the error occurs, so there are several probabilities. That means probability of no errors, probability of no errors. It means I have transmitted 0, 0, 0 and I have received 0, 0, 0. That means 0, 0, 0 I have transmitted, okay, and I have received 0, 0, 0. Similarly, if I have transmitted 0, 0, 0, I have received, 1, 1, 1, I have received 0, 0, 0. This is the probability with no error. It will be the same. Okay. So since we are taking 3 bits, that's why I'm taking the probability of error in 1 bit. This will be this one. This will be the probability. It's very simple to calculate. Similarly, probability of error with 2 bits. It is simply like this. And the probability of the error of the 3 bits, it is more dangerous, but it occurs very less because you can see it is to the power 3. That means what? If I have transmitted 0, 0, 0, that means what I have received? 1, 1, 1. That means my algorithm, what it will do without any confusion, what it will detect that it is the transmitter signal was 1, but which is not correct. So these are the probability of the errors that is going to occur for different when I am taking a 3-bit redundancy. These are the things that is going to occur. So you can see, so in the majority voting, that means it takes the decision in favor of number of ones and zeros. So we will have the correct state with the probability. We can have the correct state. When it will be, that is your detection will be correct? Only when for a 3-bit redundancy, only when at most 1 bit in error. Because you see, here 0, 1, 1 means 2 bits are in error. What I have transmitted? Actually, I have transmitted 0, 0, 0. But since 2 bits are transmitted, so the majority voting is taking decision in favor of 1, 1, 1. That means for this column, my algorithm, that is a classical error correcting algorithm, is taking decision in favor of zeros. That means it is taking decision correctly. So this is the probability you can see. So this probability plus this probability. Similarly, I can say the probability it is not taking correct decision is nothing but your 3pt square multiplied 1 minus pt plus pt cube. That is the case. So in quantum computing, this redundancy is not possible. That is cloning, no cloning theorem is there. That is, I hope till now we have learned so many things about this quantum computing. So this is not new for you. That is no cloning theorem. That means you cannot clone anything because the state of the qubits are not predictable. That's why it is not possible to clone it. That means as simple as to that of the redundancy where we have applied in classical kind of thing is not possible in your quantum computing, right? That means it says there is no device that will copy an unknown quantum state. If it is 0 state, then it tends to 0, 0 if you want to clone it, right? If it is 1 state, it will be 1, 1. But by linearity, so by linearity, if it is alpha state 0, alpha state 1, it will be alpha 0, 0 and beta 1, 1. But it is not like this, right? So this is related to your uncertainty principle that is suggested by Hudson-Bond. Similarly, some of the barriers to quantum error corrections are measurement of the error destroys the superposition. Here we are not measuring the error. That we'll see how, because as I told you in the classical problem, how can you detect the severity of any error in classical problem? By measuring the error. But here, if you try to measure the error, then you are destroying the superpositions. The superposition is required for your quantum computing. And second one is no cloning theorem prevents repetition and must correct multiple type of errors like your bit flip or phase errors, as I told you already. Other two, that is your what are the other things that we talked, like rotation and complete dephasing. These are the problems that has to be taken care. Then how can you correct continuous errors and decoherence? Because decoherence is a major issue. Since the qubit, when it is propagating, definitely there will be change in some phase. That means it is losing its coherence. So in quantum computing, coherence plays a major or vital role. So that has to be taken care. As the first thing says that measurement destroys the superposition. So let us apply the classical repetition code to a quantum state. Let's see whether what is happening. Classical repetition code to quantum state to try to correct single bit flip error. Let's see. So if it is a superposition, that is linearly, if I will say, that means 0 should be represented by 0, 0, 0. Similarly, 1 is represented by now 1, 1, 1. Let's say the middle bit, that is the second qubit, is flipped. That means your this one is 0, 0, 0 is becoming now 0, 1, 0, and 1, 1, 1 is becoming now 1, 0, 1. Now we used to measure that it is different without finding its actual value. That is, we are not going to measure it, but rather we are trying to find out without measuring it. That is our objective. So how to do that? So we need to measure the error, not the data. Right? You have to measure the error, not the data. So how to do it? So let's what was the thing that is in this process, actually a single bit is going to be represented by 3 bits, but it is, that is, cloning is not possible. So how to do it? By using some ancilla qubit. That means sometimes mostly it is the 0 bits. We can have this kind of thing. Let's see with a simple diagram. Let me explain. Let's say this is alpha or A, whatever it may be, it is transmitted, and then we will be using 2 ancilla bits. This is one, this is another, and they are by default, let's say 0, and this is also 0. Okay, so we'll do some operation, that is by using your Toffoli gate. Let's say this is the operation here. Similarly, from this ancilla bit, we'll do some operation like this and represent this as, let's say this represented is A. Okay, to avoid any confusion. So let's represent it as A. So what's how it will look like now? Now let's say this A will first let represent like this as linear combination, that is your alpha 0 and plus it is beta 1. Okay, so these two bits, that is ancillary bits, that is 0, 0 will be 2 more bits, isn't it? Okay, this will be 1, 0. This is now second 0. Our objective is to go for 3 redundancy without going for any cloning. So this will be equals to, so I'm writing here, this will be equals to, let's start. This is the first one, right? First one, this is the control. This is the control for the first bit. You can see this is the control for the first bit, right? So what I will get? I will get alpha. So it is 0 here, you see 0. And this is also 0. 0 means there won't be any change. The control is 0 and this bit is 0. So this is becoming 0, 0. Right? So plus, now when talking about this beta, now this is your control here. This is the control, isn't it? Control is still 0. That means there won't be any change. So that will be 1, 1. Okay. So let's make a parenthesis here. Now this is 1, 1. And what is remaining? 1 bit is remaining. That is 0. This third one, third is, that is 0. Now next is coming to the next, again one operation, right? So this will be becoming, again, here the control, alpha, already we are having 0, 0. Now since control is 0, this bit is 0, there won't be any change. This is becoming 0, 0, 0 plus beta, it is 1, 1, 1, 1, right? So the control is here, again it is control is here, fine, so 0. That means this is first 0 is converted to 1 is converted to 0 first, two things are there. Then it is converted to again 1. Now I am having this one, which is nothing but my AL. Okay, so in this way that I can do it. The same thing is cited here. You can see in a different way. That was the simplest way that I have told you how to generate the things. So based on that, we are going to design so many things, that is generating some error syndrome. Based on the error syndrome, we can say that which bit is in error. That is the actual practice people are doing. Okay, so the first bit of the error syndrome says whether the first 2 bits of the state are the same or different. Similarly, the second bit of the error syndrome says whether the second 2 bits of the states are same or same. This is the simplest procedure I am trying to say. Based on this, so many protocols, coding techniques are designed. So that is a different part that we have to think about. But these are the fundamental things we need to understand first. So that means the error syndrome, if the first bit says about whether the first 2 bits are in error, and second bit says whether the second 2 bits are in error. Once you understand this, then finding that error may be easy. With the information from the error syndrome, we can determine whether whether there is an error and where it is. That is important. Where it is, that has to be rectified. So for example, let's say alpha 0, 1, 0 plus beta 1, 0, 1 has a syndrome 1, 1. Has syndrome 1, 1. So if it says that this is 1 and this is 1, when the first bit is in error, what it says? The first 2 bits of the state are in, the first 2 bits of the state are in some same or different. And when we say the second 2 bits, that is second bit in bit of the error syndrome says, that is whether the second 2 bits of the state are the same or different, right? So based on that, if both are 1, which means the second bit is different. You see, when both are 1, which says the second bit is different, then we can have and correct it with some X operation on the second qubit. Some X operation that we'll see later how to introduce those X operation. But as of now, some operation we must say that we have to apply to rectify this. So what summarize we can say? We are not going to bother about the data. Rather, we should be bothered about the error so that we can preserve the superposition. So if we lose the superposition, then that leads to a very severe problem in quantum computing. So here, what we can say, we are having redundancy, not repetition, because cloning is not allowed. So this encoding does not violate the no cloning theorem. It means if it is alpha, it is 0 and beta 1, then what we are doing, we are representing as alpha 0 0 0 and beta 1 1 1, but not like this, not repetition. So we have repeated, sorry, yeah, we are not, that means, yeah, redundancy is not like that. Definitely this repetition may not be the thing, I should not write this. Anyhow, we repeated the state only in the computational basis, right? Superposition states are spread out. That is your nothing but a redundant encoding, but not repeated, which is violating the no cloning. Yes, the statement is correct, right? So we have repeated the state only in the computational basis, that is your redundant encoding, where the superposition states are spread out. It is not similar to that is your frequency spreading. It is not that. We should not get confused with that statement, right? So this is not that is your kind of thing like to your frequency spreading in your different spread spectrum techniques. It is a different thing. Now let's go with some examples so that you can have a feel of this. Let's go for a 3-qubit error correction. So the things that we learned so far, that is we are talking about 3 bits only. We can go for a better technique, that is sometimes people are going for a 9 number of bits, 5 number of bits for redundancy, so that the error correction will be more appropriate. But let's start with some 3-bit qubit error correction. So a 3-bit quantum error correction scheme uses an encoder and decoder circuit that is shown here, right? Similar to that as I told you in our previous slides. So we are using some ancilla, that is your bits. Those are means they are known to us. The state of these bits are known to us. We are using these 2 bits because these 2 bits, state of these 2 bits is known, and we are taking it 0 0. But input, the state of the input qubits, that is completely random. It is not known to us. So here the output of the encoder is nothing but the 3 qubits we are having, and these 3 qubits are going through this channel, or they are introduced with some errors, and the detector, at the detector again we are getting the reverse of the encoder process, and we are getting back our qubit, right? Now the encoder will entangle the 2 redundant qubits with the input bit. The input bit may be either 0 or 1 or a superposition of the inputs. If the input state is 0, then the encoder does nothing, so that the output state is 0 0 0. And similarly, if the input state is 1, then the encoder flips the lower states. That means this was 0 0, So when it is that is input is only 0, then since these two are 0 0, the encoder is doing nothing. It is allowing these two things to come out. That is, I am having 0 0 0. But when input is 1, so what it is making? The encoder is flipping these zeros to 1 and giving as my output state is 1 1 1. When if the input is in superposition state, that means A of 0 plus B of 1, then the output is the entangled state. And what it gives? That is A 0 0 0 and B 1 1 1. And the problem, any correction must be done without looking at the output. Sometimes while your error correction is happening, how? In general, your traditional process, people are doing error correction by observing the output only. If you say in any closed path that your a part of the output is given back to the input as feedback. So that feedback is giving some error input to it, and accordingly my algorithm is getting any adaptive algorithm getting executed. But here that process is not possible. The reason is we cannot look at the output. So the decoder looks like just like an encoder, the same thing, 3 input, and it is having same what you say the error syndrome. Sorry, your error syndrome, right? So if your error synonyms are 1 1, flip the top qubit. If the input to the decoder is 0 0 0 or 1 1 1, there was no error, so the output of the decoder is 0 0 0 will be represented as 0 0 0, and 1 1 1, if the output is now 1 0 0, the top one causes the bottom bits to flip. So what it will do? It will do to make these two bottom bits flip to 1, so that since input was transmitted as 1 1 1, and the output is also becoming 1 1 1. That is the case, right? Now consider all possible error conditions. So when A 0 0 0 and B 1 1 1 is decoded to A 0 0 0 and A 1 0 0, means what? You see, these two bits are 0 0. That means A 0. That is, there is no error, right? When there is no error, what we are getting, the similar case that we have discussed in the previous slide, this one. The presence of this one will flip these two to flip bottom 2 bits, right? So this is the case. So the top qubit is flipped, right? So that means this 1 0 0, B 0 1 1 decoded to A 1 1 1, top qubits flipped, and B 0 1 1, right? That means this is leading to A1 B 0. The case is what? You see, this is 1 1 and this is 1 1. So flip the top qubit, because as here you see that if 1 1 we are getting, then you have to flip the top qubit. So what is the top qubit? The top qubit was 1 here, it is to flip it 0, and this was 0, and you have to flip it as 1. what we are getting? We are getting the actual result. Similarly, if middle qubit is flipped, we'll get this as 1 0, and if the bottom qubit is flipped, then we'll get 0 1. So based on that, we are going to take some decisions. So in phase shift, this is one kind of error correction. Then by using your Hadamard's code gate, Hadamard's gate, your 0 is mapped like this: 1 by root 2, 0 plus 1. Similarly, 1 is mapped as 1 by root 2, 0 minus 1. So when we are saying that it is a Hadamard coding, Hadamard gate we are using, then the same procedure, only what we are doing, we are putting some Hadamard gate here at the transmitter side, and similarly at the receiver side we are also introducing the same thing, the same Hadamard codes we are using. So by doing this, in the previous case we have talked about, we have addressed the bit flipping error, and by introducing this Hadamard gates, we'll be able to go for phase shift errors, right? So how we'll be deciding at the decoder? If 1 1 shift the phase of the top qubit, if you remember here what we are doing, if 1 1 flip the top qubit, because here we are talking about the flipping error, we are not talking about any other errors. But when we are introducing this Hadamard's gate, now we are talking about the phase shift error. How to correct errors due to the phase shift, because phase shift is a big issue for us. Actually, I got my throat infection. Let me see how far I can go. Anyhow, now if 1 1 the output, then the phase of the top qubit is going to be shifted, right? So accordingly we'll go for the corrected output. So there is another coding that is called as your source qubits error correcting code. As we know that the previous two error correcting codes, that is first one is talking about what you say the flipping of the bit, and the second one is taking care of the phase. Then what this source 9 qubit error correcting code is doing, it is combining the both. So it can correct any arbitrary single qubit error. So how it looks like? It's very simple. So it looks like this. That means first the phase flip is corrected. That means it is introduced. This is the things that are designed in the transmitter side. Then the bit flip coding, and this is my quantum channel through which my signal is passed, and at the receiver the reciprocal operation we are going to do. Okay, so that now both the bit flip and phase flip can be addressed. So these are some of the very simplest things. That means instead of now 3, so here the Hadamard's gate is representing like this. Now we can think about something more. so that now bits will not be represented by only 3 bits, rather it will be represented by some more number of bits. So more operation can be thought about, so that we can get a better correcting code, and we can meet the quality of the service. I think I should stop here. Sunita ma'am.
Hello, sir.
I should stop here. My throat is not allowing to continue.
Yes, sir. Yes, sir. Sure, sir.
If anybody got any query, then I will be happy to.
Sure, sir. Participants, if you have any queries, then you can put in the chat box. Otherwise, you can write it down.
Yes.
Message in the chat box so that I can unmute you. Dear participants, if you have any queries, kindly put in the chat box.
Okay, since there is no query, then I should say thank you to all.
Thank you, sir. No queries, I think so. Thank you,
Okay.
sir. Thank you for your brief explanation about this error correcting course, about the errors that first you said, then how to correct it and all you said. Thank you, sir. Thank you so much,
Okay.
sir. Thank you for giving your time.
Thank you.
Yes, sir. No queries. Someone messaged also. Thank you,
Okay.
sir. Yeah, participants kindly fill the attendance form. Okay, before leaving the meeting, kindly fill the attendance form and then we'll update the attendance by tonight, so that in the portal you people can check your attendance. Thank you all. Now I'm going to end the session. Tomorrow, kindly join in time.
Instruction test is.
Yeah. Tomorrow test is there. So after the valedictory function, we will keep the test.
30 questions, 60%.
As you know, like as per the criteria of AICT, 60% you need to get.
From the past 4 days.
Whatever from this during this 4 days and tomorrow, these 5 days, whatever in the session, whatever you have attended, from that we are going to ask questions. So you need to attend the test. Actually, it's compulsory for everyone. Where can we check our attendance? Attendance you can check
tomorrow morning.
Tomorrow morning you can check in your portal itself.
In case
any clarification is required, then that time you can ask. Okay.
Or 4 days service we will do.
Okay. Okay, any other things? Kindly you can message to us if any queries are there. In the chat box also you can message, otherwise you can message in the WhatsApp. But this year test is compulsory and all are requested to attend the valedictory function also, because right after the valedictory function we are going to conduct the test. I think it's clear to everyone. If any queries, yeah, thank you. Okay. Okay, then I'm going to end the session. Duration of test, we will inform tomorrow, like, or by night, otherwise tomorrow morning we will inform about the duration of the test and how much mark we are going to conduct. Everything we will give you brief. We will message you regarding the test. Test is compulsory to attend. Regarding the test questions and all, we will inform you tomorrow. Duration, how much mark, everything in detail, we will inform you tomorrow. Thank you all. Now I'm going to end the session. Any queries? Anyhow, we have the WhatsApp group. You can ask me, no problem. Thank you.